Hey everyone, and welcome. In this explainer, we're going to dive deep into one of the most fundamental forces in our entire universe, heat. And we'll be using this incredible physics notebook as our guide to uncover the simple but super powerful rules that explain exactly how heat gets from one place to another.
So it really all starts with a simple question, one you've probably asked yourself 1,000 times. Why does a hot cup of coffee always go cold? And for that matter, why does a cold drink always warm up? You know, it kind of feels like magic, but I promise you, it is pure physics.
And the answer is right here, inside these amazing handwritten notes. Turns out, the flow of heat isn't random at all. Actually, it's incredibly predictable. It all comes down to just a few key principles that we are going to unpack together right now. All right, so let's jump right into our first section, the rules of heat flow. We're actually going to build the core formula that scientists use to calculate exactly how fast heat moves from a hot thing to a cold thing.
Okay, let's break this down. It turns out there are 4 key factors that decide how quickly heat moves. First, we've got A for area. Just think about it, right? A huge pane of glass is going to lose way more heat than a tiny little window. Next, you have the temperature difference. A boiling pot of water is going to cool down a lot faster in a freezer than it will on a warm summer day. Simple enough? Then there's X, which is just the distance or the thickness of the material. This is why a big, thick winter coat keeps you so much warmer than a thin t-shirt. And finally, we have K. This is all about the material itself, its thermal conductivity. You know this intuitively. A metal spoon in hot soup gets hot way faster than a wooden one, because metal is just a better conductor. Put them all together, and you've got the master equation for heat flow.
Okay, so now we know the rules that control the rate of flow. But let's look at the 3 distinct ways that heat actually travels. You can think of them as 3 different highways that energy can take to get from point A to point B.
And this simple drawing, it perfectly captures all 3 modes of heat transfer. Just look at this campfire scene. You've got conduction, convection, and radiation, all happening at the exact same time. Let's take a closer look at each one.
So first up, we have conduction. This is heat transfer through direct contact, direct touch. Imagine you're holding a metal rod and you stick one end in a fire. The heat makes the atoms at that hot end just vibrate like crazy. They bump into their neighbors, who bump into their neighbors, passing that energy all the way down the line until, ouch, it reaches your hand. It's like a chain reaction, and it's most common in solids. Next up is convection. Now this is the one that happens in liquids and gases. You've seen this a million times. When you boil water, the water at the very bottom gets hot, it expands, it becomes less dense, and it rises up. Meanwhile, the cooler, denser water at the top sinks down to take its place, gets heated, and then it rises too. This whole process creates a current, a literal physical movement of particles that carries the heat all through the pot. That's convection. And finally, we have radiation. And this one is in a class all by itself. See, it doesn't need any particles or any medium to travel through. It is pure energy just moving through space as electromagnetic waves. This is how the sun's warmth travels through the total vacuum of space to reach us here on Earth. So now that we understand those 3 highways of heat, let's focus on the most powerful one of all, radiation. And we're going to explore its most extreme, perfect form, the perfect black body. Now, when a physicist says perfectly black body, they're not really talking about the color black. It's a theoretical object, a concept. It's a body that absorbs 100% of all radiation that hits it, no matter the wavelength. And what's so fascinating is that a perfect absorber is also a perfect emitter of energy. And as these nodes point out, the sun is a pretty darn good real-world example. And this brings us to a rule that is truly mind-bending, the Stefan-Boltzmann law. Now, the key phrase on this slide is fourth power. This means the relationship here is not linear at all. If you double the absolute temperature of an object, it doesn't just radiate twice as much energy. No, it radiates 2 to the power of 4, which is 16 times more energy. It's an exponential explosion of power. This is why stars get so unbelievably hot and bright. Okay, so this isn't just some abstract theory, right? These laws are running our world every single second. Let's see them in action with a few really cool examples straight from this notebook. Let's start with a really common scenario. Imagine it's nice and cozy in your room, say 30 degrees Celsius, but it's a chilly 5 degrees outside. You've got a standard-sized glass window. So the question is, how much heat energy is just pouring out of it every single second? Well, the calculation shows a staggering 13,200 watts of energy loss. To put that into perspective for you, that's the same amount of power used by over 130 old-school 100-watt light bulbs all running at once. That is a huge amount of invisible energy just pouring right out your window. Okay, let's try another one. This time, let's make it a little more personal. See, our bodies are constantly generating and radiating heat. So how much energy does an average person radiate just by standing in a room that's at freezing, 0 degrees Celsius?
The answer is about 197 watts. Think about that. That means that right now, as you're sitting there, you are radiating heat with the same power as 2 bright 100-watt incandescent light bulbs. You are literally a walking, talking source of thermal energy.
All right, for our final example, let's go big. Let's go cosmic. We've looked at a window and a person. Now let's apply these exact same rules to the ultimate source of heat in our solar system. How much total energy does the sun radiate every single second?
The number is, well, it's almost impossible to even comprehend. According to the Stefan Boltzmann law, the sun belts out over 450 septillion watts of power. That is a 45 with 25 zeros after it. It's an astronomical figure. And yet, it's described by the exact same physical laws that explain your cup of coffee going cold. From the steam rising from your tea in the morning to the warmth you feel from the sun on your face in the afternoon, our world is absolutely governed by these invisible highways of heat. So the real question is, now that you know the rules of the road, what invisible forces will you see at work around you today?
Thank you for watching my video. Please like, subscribe and hit the bell icon.